Hi, my name is Bukihano Marali. I'm a PhD student with Queen Mary University of London and University of Genoa, and this is our presentation on workspace scaling and rate mode control for virtual reality-based robot teleoperation. Our work focuses on development of novel virtual reality-based teleoperation interfaces. Virtual reality headset and handheld controllers provide the operator with improved depth perception and more intuitive control. Conventional teleoperation often uses position-to-position mapping, where displacement of the input device is mapped to the displacement of the teleoperated robot, as demonstrated here. In VR, it looks like this. Position-to-position control can utilize the full range of operator's arm motion, which can be fatiguing. Smaller arm motions are preferable for long teleoperation sessions. It is possible to increase the position-to-position scaling gain, such that small movement of the input device will result in large robot motions. But this approach decreases positioning accuracy. By comparison, rate mode control maps the input device displacements to the teleoperated robot's speed. This allows the operator to use smaller input workspace to navigate the robot, which in turn can reduce the fatigue over long teleoperation sessions. Here is the example of rate mode control in VR. In our previous work, we have introduced a set of gestures that allow the operator to scale the virtual world. When combined with position-to-position control, changing the scale of the virtual world effectively changes the position-to-position mapping. For example, if the virtual world is scaled to twice the size of the real world, the operator's 1 meter input displacement in virtual world will translate to half-meter movement of the robot in the real world. A similar approach can be used in combination with rate mode control. In variable rate mode, we combine the conventional rate mode and virtual world scaling. Depending on the scale of the virtual world, the same input device displacement can result in different robot speeds. For example, let's say that when the size of the virtual world is the same as the size of the real world, 1 meter displacement of the input device results in 1 meter per second speed of the robot. Then, if operator scales the virtual world to the half of the real world, the same 1 meter displacement of the input device in virtual world will result in 2 meter per second speed of the robot in the real world. We have designed an experiment to find out if variable mapping improved the teleoperation performance compared to constant mapping. We asked 5 participants to perform robot reaching tasks, where they had to move the robot's end effector to randomly generate a target position as fast as possible. Each experimental trial had 10 targets, and each participant had performed 15 trials per experimental mode. We constrained participants' hands motions by asking them to keep their elbows fixed at torso to reduce fatigue. Here's an example of participant performing the robot reaching task. Each participant has spent roughly 40 minutes per experimental mode. In order to reduce the effect of fatigue on their performance, we have scheduled the constant mapping mode on day 1 and variable mapping mode on day 2. As it can be seen, some learning was transferred. However, in both modes, the learning curve flattens after the 5th trial, indicating that there was no further learning after that. Hence, we use trials 6 to 15 for analysis. Our study demonstrated that participants needed less time to perform the experiment in variable mapping mode, with 3 out of 5 participants showing statistical significance. In variable mapping mode, participants were able to zoom out to perform fast large motions and zoom in to perform slow accurate motions, which allowed them to reach the target positions faster and more accurately. This, however, came at higher workload cost. The NASA Task Load Index breakdown demonstrates that participants found the variable mapping to be more physically and mentally demanding. In post-test interviews, they have indicated that in variable mapping mode, they had to plan their sequence of actions more thoroughly, as well as move their hands with more precision. This perceived workload increase, however, could be the effect of scheduling the variable mapping mode on day 2, when participants have different, arguably more realistic performance expectations than on day 1. In conclusion, our study have demonstrated that variable mapping rate mode that adjusts along with the virtual world scale allows participants to perform robot reaching tasks faster than when using constant mapping rate mode. Participants have reported higher physical and mental demand. However, We have not observed any decrease in task completion time due to fatigue within 40 minutes of testing per participant. Hence, it is yet unclear if the increased workload constitutes a considerable drawback. The proposed variable mapping rate control mode is suitable for robotic arms and mobile robots, especially in applications that require long teleoperation sessions. This concludes our presentation. Thank you for watching.